Okay, so we now want to look at how to handle orientation. Points we discussed, you just parameterize the path. So if it's a primitive with a straight line or a circle, you can similarly write a parameterization for the ellipse without a great difficulty, or a parabola. I mean, you already know how to do that. So it's not a big problem, or for a helix. And then using the single parameter that you have, you just do a time trajectory of that, then you can go back and compute everything. Now orientation usually specified using the rotation matrix and at the end effector frame. Okay. And the reason it is done is that you roughly know which way you know exactly which way you want the axis. So if you are drilling, you know that at least there is one axis which has to go along your axis where you want to drill. The other axes are not very important as long as you have one axis correct. I mean because other axis anyway the drill end keeps rotating. So similarly, if you are doing an insertion of a non-cylindrical piece, then you at least know two orientation directions. So you can, using that, you can specify the full rotation matrix. And then the only catch is, so we have unit vectors, right? We have this unit vector which is there. So simplest thing is that you can take the unit vectors, you can cascade it, that will give you a longer vector of dimension 9 and you can try and parameterize that. Except that we know that it will not work. Why will it not work? Because if you do a interpolation of the unit vectors describing the initial and final orientations, then when you do the interpolation, then the intermediate ones are not guaranteed to be orthonormal. You remember that when we did the rotation matrices, we said that the columns are normal to each other, the rows are normal to each other, they are all unit vectors, and the product of the any two will give you the third one with a plus or minus sign. So all these properties have to be satisfied by the rotation matrix. If it is not satisfied, the basic problem we will end up to is interpolating it is fine, but later on after that we have to do inverse kinematics to get it to the joint space where we will do the control. So if we get arbitrary rotation matrix which is invalid, we will not be able to do the inverse kinematics, it will be inconsistent. So we will end up in trouble. So that is where the problem is. So we have got to handle this small issue and we are done with being able to interpolate. Now so this is not a new problem, right? People have been working on it for roughly 300 years now. So Euler worked on this problem, and so what he came out with is that you can represent a rotation in space. So it is equivalent to 3 combined rotations about orthogonal axis or one's orthogonal axis repeating exactly one axis. So if you look at this Euler conventions, this is about OZ, so there is XYZ and UVW coordinate systems. Okay. So this one has a Z axis and the W axis. This is Z and W, and oops, this one doesn't have anything in common. How is that? Oh, roll, pitch and yaw. Okay, this is actually okay. This is the other thing. This is called the Euler angle system, but it's not the Euler. This is, that's why this is called the roll, pitch and yaw system. This is what is called the Tait-Brand angles. Okay. Now this is composed of rotations in 3 different axes. Now there is a lot of mathematics which goes into trying to determine that there exactly you can have 6 possible rotations repeating exactly one axis. There are also exactly 6 possible rotations in which you can use rotations about different axes. Okay. So that you can show mathematically. So, you can use any of these systems, of these 12 systems, and you can parameterize, essentially get a scalar parameter equivalent for the rotation. Now, how do you get that? So, if you have a rotation matrix, if you have say this Euler 1 system, okay, so it is this sequence of rotations and then this lands up in this kind of a rotation matrix 3 by 3. And you can go the other way around also. There is a fairly easy way of determining how to go from here to here. Okay. And there is a small advantage of the Bryant angle system. It just takes care of a singularity which is there in the Euler system. Okay. In the Euler system, there is a one non-uniqueness problem which is handled more elegantly in the Bryant system, the Rolle-Picciott system, which is this one. So, when you are working trying to parameterize these rotations in space, you can use any angle convention. It can be converted into a rotation matrix. So, you can just make your pick, whatever you feel comfortable with, okay. And you will find enough literature including Wikipedia which will give you what all these matrices, and enough books around which will tell you what these matrices are and how to go from one to the other one. So, if you have this matrix, if you have entries of the matrix, values for these, you can easily find out what this phi theta psi will be. Okay. So, that is not a problem. Now, so what you do now is that you take these Euler triplets phi theta psi and you just, since you are an ordered set of scalars is called a vector in, well, it is one notation for a vector. So, you define this vector phi e. So, now this phi e moves along this virtual segment in 3 space going from initial value to the final value. So, it does not matter whether it is x, y, z coordinates, and we can actually see as a path in space, but instead of x, y, z, if it is phi theta psi as a 3 coordinates, it will trace a mathematical path in space. It does not correspond to a physical path in space as we see it. Okay. So, what you can then do is you can pick any interpolating function, but if you use polynomial blended function, then you get continuity. So, you simply write it in this form, okay, phi I plus s upon the final minus phi I divided by this. So, you can define phi dot as this and then phi double dot as this. So, you can define velocities, accelerations. So, what will happen is you have a vector you had a path in space and you are simply parameterizing that path in space using S. You know the method to do that using the path length. So, it is a virtual path length again which does not physically correspond to a tape measure, but does not matter. So, mathematics is very similar to, well, let me just flick back. See, we did this, right, we reduced a circle into this form, a linear segment into this form. So, this is identical, the form I am showing today is identical to this, except that instead of this Pf and Pi being having components x, y, z which are linear, which are the Cartesian measures, they are just this Euler angles. So, the mathematics is identical. You just have to get used to it, and then you can generate these triplets. Now, once you have obtained the intermediate value of this vector phi e, you convert it back into the rotation matrix, right, and then you can cascade, do the inverse kinematics, and then do the control at the joint level. So, that is the method which you use. Now, there is another method. So, hopefully you will remember this slide, right, which many of you, finite screws, right, from which you had a little question in the earlier minor. And so, starting with the fact that many of you forgot that from this you can only find the magnitude of theta, right, and finding the sine of theta is a more complicated thing, but anyway. So, here is another method because I want to move from an initial position to a final position. And I already know that for this kind of a structure, what can I find? I can find this rotation value theta, including the sign, and I can find this vector about which the rotation happens, the rotation axis. I can do that. Now, if I have done this, so this is the formal way of writing it down. So, you have you are defining the rotation matrices, and you interpret this as a vector where the theta varies with time, and this the rotation axis that we have, that does not change, it is a fixed vector. Okay, it's a simple structure, and theta evolves over time. So, all you need to do is assign a timing law to theta. So, exactly like a single axis problem, you assign a timing law to theta with theta 0 equal to 0 and theta Tf is equal to theta f. Actually, why should this be 0? It should be theta I. Well, no, actually 0 is fine. Sorry, what happened? Yeah, starting with 0 and going to the final rotation. So, you get theta f. And so, using this method, suppose in addition to just specifying rotations, the orientation, you say at this point I wanted the angular velocity to be this, at this point I want the angular acceleration to be this, we have methods of specifying them also, right. In interpolation, sometimes it is needed to specify not only position but also velocities. Similarly, not only angular position but also angular velocities may need to be specified in rotation. So, if you do that, then you can write expression for the angular velocity, which is again basically theta dot Ri, and then the angular acceleration, which is theta double dot Ri, because Ri is a fixed vector. So, there is no differential of it. So, only the scalar parameter get differentiated. So, very easy to obtain angular velocities and angular accelerations if you need to specify it. So, once you are given all these things, it is then not a big deal again. So, given a path and a trajectory in the operational space, P t and phi t or RIT, any of the three forms, this is the position, and the rotation in terms of either the Euler angle form or the rotation form that we dealt with. You then use inverse kinematics to find the corresponding trajectory in the joint space, and then at the joint space you do micro interpolation to enhance the dynamic performance locally. Now, both of these are computation intensive processes. So, I will repeat this again, I have already mentioned in the previous class. So, you can only do this so often, but given modern computers you can easily do it at update rate of 60 hertz. Most mechanical systems run at 1 hertz, 10 hertz of that order. So, you are pretty fine, but this can be done much faster also. I mean, computers have become so fast now that, and you do not even need a DSP toolkit or something. So, if you have a DSP in your system, then you can do this much quicker, these kind of things. In fact, you can code this into microcontroller itself. I mean, this level of mathematics is not very difficult. I will take that statement back. It will be a little bit of a problem implementing all of this inside a microcontroller. You need a slightly bigger system for that, but this you can do at the microcontroller level. So, you do this in a computer or a DSP, and then you pump it back into the microcontroller and you are in business. So, with this I have given you enough tools to use most robots, which will be available to you. Okay. including these kind of interpolation stuff is relevant also to robots which move around and things like that for path planning. So you can do most of the stuff using this.